Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
So I want you to imagine standing right in the middle of a pitch-black football stadium.
Okay, totally dark.
Right. And at the far end of the field, someone just flips a switch, and every single high-intensity floodlight turns on simultaneously.
Oh, wow.
And they're all aimed directly into your eyes. Like, it is blinding physical pain, right?
Yeah, that sounds awful.
It gets worse. Now, someone hands you a camera, and your job is to take a perfectly clear, sharply focused photograph of a single firefly.
A firefly in front of the floodlights.
Exactly. Buzzing about, 1 inch away from the glass of one of those lights.
That's literally impossible.
Right. You have to capture the faint, delicate glow of this tiny bug through this actual wall of light that is actively overwhelming your retinas and your camera sensors.
And that right there is exactly why we don't know if we're alone in the universe yet.
Exactly. That impossible, blinding task is the reality of modern astronomy. We've been staring at the night sky for millennia, asking if there's life out there. Mm-hmm. But we're effectively just staring straight into those floodlights.
Yeah, the fireflies are out there, but we just can't see them.
Right. And that's really what we're getting into today, because the transition happening right now in astronomy is it's wild. Mm-hmm. Wondering about those fireflies is no longer enough.
No, it's not.
Yeah.
For most of human history, asking, are we alone? That was a question strictly for philosophers.
Or theologians or science fiction writers.
Exactly. You'd sit around a campfire, look up, and just guess. But the era of guessing is basically over.
Which is so exciting.
It really is. That profound existential question has officially been translated into an engineering problem.
An engineering problem. I love that.
Right. We're no longer debating whether life might exist. We are physically building the machines to filter out those floodlights and get a definitive, undeniable photograph of the answer.
Which means we really need to understand the sheer, brutal physics standing in our way.
Yeah, the physics are not very forgiving.
No, they aren't. Because if we want to find life, astrobiologists are very clear that we need to look for planets in the habitable zone, right?
Yeah, the Goldilocks zone.
Exactly. Not too hot, not too cold, just right for liquid water. But when you actually break down the mechanics of a solar system, that requirement, the habitable zone, is the exact thing making this almost impossible.
It really is. To understand the obstacle, you have to look at the geometry of it all.
Okay, break that down for us.
So if a planet is too far from its host star, any water on the surface just freezes solid.
Right, you get an ice ball.
Yeah. And biochemistry, as we understand it, just grinds to a halt. But if it orbits too close, the stellar radiation boils the water away into vapor.
And the atmosphere just gets stripped away, right?
Exactly. You're left with a scorched rock. So the habitable zone is this really narrow, specific orbital band where a rocky planet can actually maintain liquid water on its surface.
But because it's so narrow and so close to the star.
Right, because it's relatively close, any planet inside that band is completely engulfed by the star's glare from our vantage point, light years away.
So proximity is the prerequisite for life, but it's also the ultimate barrier to us seeing it.
That's exactly it. And you have to factor in the scale of brightness, too.
Oh, man, the brightness scale is just absurd.
It's incomprehensible. A host star, like something similar to our sun, is typically 10 billion times brighter than the Earth-like planet orbiting it.
10 billion.
Yeah. The star is a raging nuclear furnace, right? Constant fusion.
And the planet is just a rock.
Exactly. The planet produces zero visible light of its own. It only reflects a microscopic fraction of the star's light back out into space.
Which is its albedo, right?
Right, albedo. Earth, for example, reflects roughly 30% of the sunlight that hits it.
Mostly from, clouds and ice and stuff.
Mostly clouds and ice, yeah. So you are looking for an object that is 10 billion times dimmer than the nuclear fireball sitting right next to it.
10 billion to 1. The human brain literally cannot comprehend a ratio like that.
No, it can't.
We understand 100 to 1.
Yeah.
Maybe 1,000 to 1. But 10 billion to 1 is a number so vast it just registers as a wall of noise.
And in the realm of optical engineering, that ratio is your ultimate adversary.
Because the sensors just get overwhelmed.
Right. When you point a highly sensitive space telescope at a distant solar system, You are trying to collect these incredibly rare, precious photons bouncing off that tiny planet.
The firefly.
Firefly. But those few planetary photons are traveling alongside an absolute tsunami of stellar photons.
Just a wave of light.
And when that wave hits the telescope's sensors, the star's light instantly saturates the image. It blows out the exposure, creates massive lens flares, and just buries the planet in digital noise.
See, I look at a problem like that, and my brain instantly searches for a brute force, low-tech solution.
Yeah. Like what?
Like if I'm driving down the highway and the sun is blinding me, I just reach up and pull down the sun visor.
Right, yeah.
Or if I'm outside trying to watch an airplane fly near the sun, I just hold my thumb up, block the sun, and suddenly I can see the plane.
A physical block.
Exactly. We know exactly where the star is in the sky. We have these multi-billion-dollar space telescopes. Why don't we just engineer a highly precise mechanical thumb to block the star's light?
Well, it's funny you say that because that is the most intuitive approach, and it's actually the foundational technology we've used for decades.
Wait, really? We do have a mechanical thumb?
We do. It's called a coronagraph.
A coronagraph, okay.
Yeah, the concept was actually invented way back in the 1930s by a French astronomer named Bernard Liot.
In the 30s? Wow.
Yeah. He wanted to study our sun's corona, its outer atmosphere, but the main disk of the sun was just too bright.
So he just blocked it?
Exactly.
Yeah.
He put a physical mask, just a tiny, precisely machined opaque disk inside his telescope, directly in the focal plane where the image of the sun forms.
Okay, so he basically created a tiny artificial solar eclipse inside the instrument itself.
You nailed it. That's exactly what it is.
Well then, problem solved. We just need to put a coronagraph in a space telescope, block the distant star, and photograph the planets orbiting it. Easy.
If only it were that easy. The physics of light simply do not allow it to work perfectly.
Because it's light, and light is complicated.
Right. If light behaved entirely like a stream of tiny independent bullets moving in perfectly straight lines, a physical block would work flawlessly.
The bullets hit the mask and stop.
And the bullets that miss the mask pass through to the camera perfect. But light doesn't just act like a particle.
It's a wave.
It propagates as a wave. And waves do incredibly frustrating things when they encounter an obstacle.
Oh, right. They bend. I remember learning this in high school physics.
Yeah, diffraction.
Right. If a wave hits a barrier, it doesn't just cut off in a clean straight line.
Exactly. Think about ocean waves rolling into a harbor and hitting a concrete breakwater. The water doesn't just stop perfectly behind the wall. The waves curl, they wrap around the edges of the concrete, and they create these new complex ripple patterns in the supposedly calm water behind the barrier.
Right, the water still gets turbulent back there.
That's diffraction. So when the starlight enters the telescope and hits the edge of that physical coronagraph mask, the light waves bend right around the edge of it.
Oh, wow. So they bleed into the exact dark zone where we're desperately trying to find the planet.
Exactly. Even with a physical shield perfectly in place, the star's light is sneaking around the edges.
That is so frustrating.
And the crazy part is, diffraction is only half the battle.
There's more.
Oh, yeah. The other, arguably more devastating problem comes from the telescope itself.
What do you mean?
Specifically, the microscopic imperfections in the telescope's optics.
Okay, wait, let me push back on that for a second.
Sure.
When we talk about modern space telescopes, we are talking about the most meticulously engineered, flawlessly polished surfaces ever created by humanity, right?
They are incredible, yes.
I mean, the mirrors on these things take years to grind and polish. They're tested in vacuum chambers. Are you telling me they still have flaws?
Well, the concept of flawless changes depending on the scale you're working at.
Okay, fair point.
When optical engineers polish a primary mirror for a space telescope, they are smoothing the surface down to the nanometer level, and a nanometer is 1/1000th of a meter. It's roughly the width of a few atoms.
So practically perfect.
To the human eye, yes. To almost any standard of measurement, these mirrors are perfect, but they are not mathematically perfect.
Because nothing is.
Right. There will always be residual surface errors, like a sub-nanometer bump here, a microscopic dip there.
A bump the size of a molecule, that actually matters.
It matters massively. When the wavefront of light from the star hits that primary mirror, it should ideally reflect uniformly. But when it hits that sub-nanometer bump,
it gets thrown off.
Yeah, that tiny fraction of the light wave is delayed or advanced by just a fraction of a wavelength, so it scatters.
Oh, I see.
And this scattered light bounces through the rest of the telescope. So when it reaches the final image, it doesn't look like a smooth wash of light.
What does it look like?
It forms this chaotic, complex pattern of bright and dark spots. We call them speckles.
Speckles.
Yeah, and these speckles dance all around the coronagraph, spilling directly into the area where the exoplanet should be.
This sounds like an absolute nightmare scenario.
It's an engineer's worst nightmare, honestly.
I mean, you launch this incredibly expensive piece of machinery, right? A million miles into space, and an imperfection the size of an atom creates a lens flare that completely blinds you to the planet you're looking for.
That's the reality of it.
But surely the coronagraph catches most of it, right?
Yeah.
Like, how much light is actually leaking through these speckles?
Let's run the math, because this is where the sheer brutality of that 10 billion to 1 ratio really reveals itself.
Okay, hit me with the math.
So this scenario comes directly from Stephen Eikenberry.
The professor at the University of Central Florida, right?
Right. He's a principal investigator specializing in tackling this exact problem. So let's assume your engineers are absolute geniuses.
Okay, geniuses. Got it.
The coronagraph and the mirrors are so incredibly well designed that they successfully block 99.9999% of the starlight.
I mean, if an engineer tells me a system operates at 99.99999% efficiency, I'm breaking out the champagne.
Right.
That sounds like a total absolute victory.
It sounds like a triumph until you remember the baseline.
The baseline. Ooh, the star is 10 billion times brighter.
Exactly. So you let 1 part in a million of that starlight leak through. 10 billion divided by 1 million is 10,000.
10,000, wow.
Yeah. The leaked starlight, that microscopic 1 in a million error caused by diffraction and atomic scale bumps, is still 10,000 times brighter than the faint exoplanet you're trying to photograph.
So you're still completely blinded.
Completely. Your planet is buried under a mountain of scattered light. And the worst part is, the speckles look exactly like planets.
Oh.
Yeah. And there are thousands of them in the image. Eikenberry is very blunt about this reality. His exact words regarding this math are, quote, "You're doomed."
You're doomed. That is, I mean, we really are fighting a war on 2 impossible fronts here.
We really are.
On the macro scale, you have a nuclear fireball that is 10 billion times brighter than your target. Yep. And then on the micro scale, you have a physical shield that leaks because light waves refuse to travel in straight lines, and your mirror has a bump on it smaller than a strand of DNA.
It's a lot to deal with.
How on earth do you fix a leak you can't even physically see?
Well, if you accept that you cannot build a flawless physical shield and you can't polish a mirror to mathematical perfection,
Which we clearly can't.
right, then you have to change your entire approach. You have to stop relying entirely on static hardware.
Okay, so what do you do instead?
You must develop a dynamic system, something that can measure the leaked light and correct it in real time, actively smoothing out the wavefront before the final picture is taken.
Active correction. Okay, I know ground-based telescopes use something called adaptive optics to deal with the Earth's atmosphere.
Exactly, yes.
Because the atmosphere is turbulent, it makes stars twinkle, so they use special mirrors that change shape rapidly to cancel out the twinkling.
Spot on.
But space telescopes don't have to deal with the atmosphere. They do, however, have these microscopic mirror bumps and thermal shifts we just talked about. Don't we already put adaptive optics on space telescopes to correct for these internal errors?
We do. We use deformable mirrors in modern space telescope designs.
Okay, how does a deformable mirror work?
Basically, it has hundreds or even thousands of tiny actuators pushing and pulling on the back of a very thin sheet of glass.
Like little pistons.
Exactly. And by changing the shape of the mirror by just a few nanometers, you can counteract those bumps on the primary mirror and flatten the wavefront of light.
That's brilliant. So that solves it.
Well, here is the critical flaw. A deformable mirror is useless if it doesn't know exactly what shape to take.
Oh, it needs instructions.
Right. It needs a sensor to tell it where the light is distorted. It needs to know where the leaks are. And this brings us to one of the most maddening architectural problems in modern astronomy.
Okay, I'm braced. What is it?
Non-common path aberrations.
Non-common path aberrations. Okay, we need to break that down because it sounds like the crux of the whole failure.
It really is. Let's trace the journey of a single photon through a space telescope.
Okay, following the photon.
The light enters the aperture, hits the giant primary mirror, bounces to a smaller secondary mirror, and makes its way deep into the optical assembly.
Bouncing through the machine.
Right. Eventually, the light hits a beam splitter. This is a piece of glass that lets some light pass through while reflecting the rest.
Okay, it forks the road.
Exactly. In traditional telescope architectures, a small percentage of the light is split off here and sent to a wavefront sensor.
And that sensor is the thing checking for errors.
Yes. This sensor analyzes the light, detects any distortions caused by the primary mirror, and sends a signal to the deformable mirror to fix the wavefront.
Okay, so the sensor checks the light, diagnoses the microscopic bumps, and tells the system to correct itself. That sounds like it should work perfectly.
The problem is what happens to the rest of the light.
The light that didn't go to the sensor.
Right, the main beam of light, the science beam. It continues past the beam splitter, passes through the coronagraph, and travels through a final series of lenses and mirrors before it finally hits the focal plane.
And the focal plane is where the actual camera is.
Yes, the main science camera where the photograph is taken. That final stretch of the journey, the physical space between where the sensor split off and where the camera sits.
That's the non-common path.
Exactly, because the sensor is on one path and the camera taking the picture is on a completely different path.
They aren't sharing the same road anymore.
Precisely. And in the freezing vacuum of space, things are never entirely static. A telescope experiences these tiny thermal fluctuations as it moves in and out of the sun's shadow.
So the metal is expanding and contracting.
Just by fractions of a millimeter, but yes. And you have spinning reaction wheels that keep the spacecraft pointed, which create microscopic vibrations.
And all of that adds up.
All of these environmental factors introduce new distortions, new aberrations into the light as it travels through that final non-common path.
But the sensor has already done its job. It checked the light way back at the beam splitter.
Yes.
It has absolutely no idea what happens to the light during that final stretch.
It is entirely blind to it. Stephen Eichenberry uses this brilliant analogy to explain this structural blind spot. He calls it the dirty bedroom problem.
The dirty bedroom. I like that. Explain that one.
Okay, imagine you own a beautiful house.
Yeah.
And your singular obsession is keeping the master bedroom flawlessly clean.
Okay, pristine white carpet.
Exactly. You do not want a single speck of dust on that white carpet. So you install a highly advanced security camera in the hallway leading up to the bedroom.
To monitor the path.
Right. You monitor every person who walks down that hallway. You check their shoes. You make sure they wipe their feet. You are rigorously monitoring the approach. But you don't have a camera inside the bedroom itself.
Ah, so you watch them walk down the hall perfectly clean,
Right.
but right at the doorway, they step in a microscopic puddle of mud.
Or dust falls off their jacket as they cross the threshold.
Right. And because you're only looking at the hallway, you have absolutely no idea they're tracking dirt all over your pristine white carpet until it's too late. The final destination is unmonitored.
The unmonitored bedroom is the non-common path. The wavefront sensor checked the light early on, but the light picked up optical dirt aberrations in the final few inches of glass and vacuum right before hitting the camera.
Wow. And because those aberrations go uncorrected, they just ruin the final image.
Yep. The speckles bloom, the contrast is destroyed, and the exoplanet vanishes.
So the obvious, purely logical solution here is just put a camera in the bedroom, right?
It sounds so simple.
If the problem is that we aren't looking at the final destination, why don't we just monitor the light at the exact spot where the final picture is taken? Why is that so difficult?
It is intensely difficult because of the fundamental rules of quantum mechanics and something called photon starvation.
Photon starvation, meaning there's just not enough light.
Right. When you are trying to photograph an exoplanet, you're not dealing with a flood of light. You might be collecting only a few individual photons from that planet every minute.
Oh, wow. Just a trickle.
It is incredibly faint, delicate information. If you try to place a sensor at the focal plane to measure the wave properties of the light, well, traditional sensors require you to absorb or manipulate that light to measure it.
And if you measure it, you change it.
Exactly. By measuring it, you alter it. You degrade or completely destroy the very planetary photons you just spent billions of dollars trying to collect.
So you need a way to look into the bedroom without turning on the lights and ruining the long exposure photograph.
That's the paradox. You have to measure the wave without collapsing the delicate signal.
That feels physically impossible. But I'm guessing this is exactly where the narrative shifts from the agonizing problem to the actual technology being built to solve it.
It is. This is where we introduce the system designed to look directly into that dirty bedroom.
Let's hear it.
Enter PEEPSS.
PEEPSS. PEEPSS. I have to say, astronomy has a long, proud history of twisting words to make catchy acronyms. What does this one stand for?
It stands for the Photonics-Enabled Exoplanet Spectroscopic System.
Okay, that's a mouthful.
It is. It's a research initiative developed by a consortium of scientists, heavily anchored at the University of Central Florida's College of Optics and Photonics, which is known as CREOL.
So what does PEEPSS actually do?
PEEPSS was conceived to solve the dirty bedroom problem definitively. Its entire purpose is to perform wavefront sensing directly at the telescope's focal plane.
Right at the finish line.
Right at the finish line.
So it monitors the shape and quality of the light waves at the exact location where the scientific camera sits.
Exactly. It monitors the complete, unabridged optical pathway. There is no non-common path anymore because the sensor and the science camera are effectively sharing the same physical destination.
That's incredible. So the system sees the dirt in the bedroom in real time.
Yes. It measures those microscopic distortions that emerge after the coronagraph, and it feeds that data back to the deformable mirrors at thousands of times per second.
Actively patching the leaks.
Yes, before the speckles can form and overwhelm the faint signal of the planet.
But wait, you just told me a minute ago that putting a sensor at the focal plane would destroy those faint planetary photons?
I did.
So how does PEEPSS measure the light without ruining the picture? This is where the cross-disciplinary nature of this project comes in, isn't it? Because they aren't just using traditional telescope mirrors anymore.
This is the crux of the revolution right here. PEEPSS is the bleeding edge of a rapidly growing, highly specialized field called astrophotonics.
Astrophotonics.
Yeah. To solve an astronomical problem, they actually had to abandon traditional astronomy and look to a completely different industry.
Which one?
Global telecommunications.
Telecommunications, as in like the internet.
Exactly as in the internet. For the last 50 years, traditional astronomy has been obsessed with building bigger glass mirrors and larger bucket-like digital detectors to just catch as many photons as possible.
Kicker's better.
Right. But over in the telecom industry, engineers were fighting a completely different war. They were trying to figure out how to transmit massive amounts of data, phone calls, internet traffic, streaming video across oceans using light.
Oh, right. Fiber optic cables.
Yes. They developed incredibly sophisticated fiber optics. They learned how to route light through hair-thin strands of glass, how to split it, combine it, and manipulate its phase with virtually zero loss of information.
They basically mastered the absolute control of light on a microscopic scale.
That's exactly it. Astrophotonics is the realization that if we take these highly advanced, perfectly refined light-manipulating technologies from the telecom world and we plug them into the focal plane of a space telescope,
we can do things normal mirrors can't.
Exactly. We can perform optical feats that traditional mirrors and lenses are physically incapable of doing.
It's like taking the engine management system from a Formula One race car and installing it into a deep-sea submarine.
I love that analogy.
You're taking high-performance engineering from one environment and using it to conquer a completely different frontier.
And doing that requires a very specific type of scientific collaboration. You can't just have astronomers working on this. You need people who really understand the deep physics of glass fibers.
Which explains the team they've built.
Right. That's why the brain trust behind PEEPSS is so unique. You have Stephen Eichenberry leading the astronomical application, but he's working alongside a team of hardcore photonics experts at UCF.
People who have spent their lives on fiber optics.
Yeah, people like Rodrigo Amezcua Correa, Miguel Bondres, and Jose Enrique Antonio Lopez. Their foundational career-long expertise in fiber optics is the engine making this whole thing possible.
That's amazing.
And you also have graduate students like Genevieve Marquez and Liza Fernanda Quinn Reyes, who are literally in the clean rooms fabricating these microscopic glass devices by hand.
Wow. Fabricating them by hand. It's a massive merging of disciplines. And it's a global effort too, right? I know UCF is partnering with the University of California, Santa Cruz, and the Space Telescope Science Institute.
Right, the organization that operates the Hubble and James Webb telescopes.
Exactly.
They're also working with international partners, most notably the University of Sydney in Australia.
Why Sydney?
Well, the University of Sydney connection is critical because, as Eichenberry points out, there are really only two major hubs in the entire world doing cutting-edge work on the specific photonic technology at the heart of PEEPSS.
Let me guess. UCF and Sydney.
Exactly. This is not off-the-shelf technology. This is true frontier science.
Which brings me to the physical hardware.
Okay, let's get into it.
We've established the problem, the dirty bedroom. We've established the solution, PEEPSS at the focal plane.
Yeah.
And we know they're using telecom fiber optics to do it. But what is the actual physical device doing the work?
Right.
Like if I walk into the CREOL lab right now, What is the secret weapon they are building to capture this light and fix the leaks without destroying the planet's image?
The technological marvel at the absolute center of this entire endeavor is a device called a photonic lantern.
A photonic lantern?
Yes.
I mean, that sounds like an artifact from a fantasy novel,
Yeah.
not a piece of space hardware. What physically is a photonic lantern?
To really appreciate the photonic lantern, you first have to understand the tragic flaw of the digital cameras we currently use on telescopes.
Okay, what's wrong with our current cameras?
When a standard digital sensor, whether it's in your smartphone, a DSLR, or the James Webb Space Telescope takes a picture, it acts like an array of incredibly tiny buckets. Yeah. Each pixel is a bucket. When light hits the sensor, the bucket measures how many photons fell into it. It measures the intensity, the brightness.
A bucket of photons. So the more photons that land, the brighter that specific pixel is on the final image.
Exactly. But light is not just a collection of particles dropping into a bucket. It is an oscillating electromagnetic wave.
Right, the wave-particle duality.
Right. It has peaks and it has valleys. It has a property called phase, which tells you exactly where the wave is in its oscillation cycle at any given moment in space and time.
Okay, phase.
But traditional pixel detectors are what we call square law detectors. They are physically incapable of measuring phase.
So they just ignore it.
The moment the light hits the bucket, the phase information is destroyed. All the intricate, detailed data carried by the geometry of the wave itself is permanently wiped out, and you are left only with a brute force measurement of total energy.
Let me try to wrap an analogy around this, because throwing away the phase of a light wave feels like a catastrophic loss of information.
It really is.
Let's imagine you're trying to study a massive symphony orchestra playing this really complex piece of classical music.
Okay.
Using a traditional telescope camera is like taking a silent black and white photograph of the orchestra from the balcony.
Oh, I see where you're going with this.
Right. Like you can see the violins, the cellos, the brass section. You know they're playing music because you can see the bows moving, but you cannot hear the music.
You just have the visual intensity of the scene.
Exactly. You get the outline, but you completely lose the intricate overlapping waves of sound.
That is an incredibly accurate way to frame the loss of data. You know energy is present, but you have no idea how that energy is structured.
So if a traditional telescope is a black and white photograph of the orchestra, what does the photonic lantern do?
A photonic lantern is like walking down to the stage and handing an individual, highly sensitive microphone to every single musician in that orchestra.
Oh, wow.
It records the isolated, multi-track audio of every single instrument. It captures the actual phase and frequency of the sound waves. So when you use a photonic lantern on a telescope, you aren't just catching photons in a bucket, you are mapping the exact shape and phase of the starlight as it hits the focal plane.
But physically, how does a piece of glass act as a microphone for light waves? Like, what does this thing actually look like?
Physically, it is a masterpiece of precision glassworking. The process starts with several single-mode optical fibers.
Single mode.
Yeah. A single-mode fiber is an incredibly thin strand of glass. The core is only a few microns across, thinner than a human hair.
That is tiny.
Because it's so narrow, light can only travel through it in one specific path or mode. It forces the light to behave perfectly, locking in its phase.
Okay, so you have these ultra-thin, perfectly disciplined glass hairs.
Exactly. You take a bundle of these single-mode fibers, maybe a few dozen of them, and you group them tightly together inside a larger glass tube.
Okay, bundled up.
Then you place this bundle into a specialized machine that carefully, meticulously heats the glass until it softens.
And then what?
As it heats, the machine slowly pulls and stretches the glass, tapering it down. As it tapers, the individual fibers melt and merge together into one larger multi-mode fiber at the front end.
Oh, so it looks like a microscopic glass funnel.
Yes.
You have a wide opening at the front that tapers down, splitting into dozens of tiny individual hair-like fibers at the back.
Exactly like a funnel.
Yeah.
Now think about the messy, distorted starlight, the speckles caused by those microscopic bumps on the telescope mirrors.
The dirt in the bedroom.
The dirt.
Yeah.
When that chaotic light enters the wide, multi-mode end of the lantern, it's a tangled mess of overlapping waves.
Right.
But as the light travels down the narrowing funnel, thermodynamics and wave physics take over. The device forces that complex light to slowly separate and transition into the individual single-mode fibers at the back end.
Wait, let me stop you there. If you're taking this incredibly faint, precious light from an exoplanet light that traveled for dozens of light years, and you're literally splitting it up into a bunch of tiny individual fiber optic threads.
Yeah.
Aren't you just diluting the light? If the planet is already impossibly dim, how does spreading its light even thinner help us see it better? Aren't you making the problem worse?
That is the exact counterintuitive hurdle that astrophotonics has to overcome. It totally feels like you're diluting the signal, but you aren't actually losing photons. You're organizing them.
Organizing them.
Yeah. The transition inside the photonic lantern is what physicists call an adiabatic transition.
Adiabatic.
Because the tapering is so gradual and so perfectly smooth, no information is lost to the environment. The total energy is completely preserved.
Okay.
But more importantly, the phase information, the exact shape of the incoming wave, is mathematically mapped across the different fibers.
So it untangles the mess.
Exactly. The lantern untangles it. It separates the complex incoming starlight into individual, clean optical channels, preserving all the phase data that a traditional camera would have instantly destroyed.
So we went from just catching water in a flat bucket, where all the ripples smash into each other and disappear,
to using a funnel that elegantly separates every single ripple so we can measure exactly how the wave is moving.
Yes.
The data that conventional systems just throw in the trash, the photonic lantern elegantly preserves.
That is deeply fascinating.
Yes.
But it naturally forces the next question.
Which is?
Now that we have all this extra wave and phase information preserved in these tiny glass fibers, what do we actually do with it? Like, how does knowing the phase of the light help us see an alien planet hidden in the glare?
This is where we bring in the final piece of the puzzle. Having this new, incredibly detailed phase data unlocks a radically different approach to processing astronomical images.
Different how?
It allows researchers to move into a highly advanced computational realm known as quantum-inspired imaging.
Quantum-inspired imaging. We are stacking some very heavy scientific concepts today.
We really are.
Fiber optics, diffraction, and now quantum-inspired algorithms. How does this actually filter out the starlight?
The core concept relies on wave interference. Because the photonic lantern preserved the phase information of the light, the computer now knows exactly how the starlight waves are behaving.
It knows the exact geometry of the wave.
Right. It knows where the peaks are and where the valleys are, and once you know the exact shape of a wave, you can mathematically manipulate it.
You can cancel it out, like noise-canceling headphones.
Exactly like noise-canceling headphones. How do those headphones work on an airplane?
They have a small microphone that listens to the low-frequency rumble of the jet engines, right?
Right. And a computer chip inside the headphones analyzes the phase of that sound wave, and then a speaker generates a new sound wave that is the exact opposite phase.
The mirror image or the negative of the engine noise.
Yes. And when the peak of the engine noise aligns with the valley of the headphone noise, the two waves experience destructive interference.
They physically cancel each other out, leaving you in silence.
And we're doing that with light.
We are doing that with light. That is blowing my mind.
We're doing it digitally. With quantum-inspired imaging, because we have the isolated phase information of the leaked starlight recovered by the photonic lantern, we can use advanced algorithms to mathematically process the data.
So you generate the anti-glare.
We calculate the exact inverse of the star's speckle pattern and digitally apply destructive interference. We essentially cancel out the complex glare of the star.
Unbelievable.
We strip away the 10,000 times brighter noise, layer by mathematical layer, until the only thing left in the data is the incredibly faint, hidden signal of the exoplanet that was buried underneath it all.
If we step back and just look at the entire architecture of this solution, it is a breathtaking sequence of specialized engineering.
It's an absolute gauntlet.
It really is a gauntlet that the light has to run. First, the light enters the telescope, and you use the physical coronagraph mask to block out 99.9999% of the main glare.
Step one, yeah.
Then, to handle the 1 in a million leak caused by diffraction and atomic mirror bumps, you use the PEEPSS system.
Right, looking into the dirty bedroom.
You look right into the dirty bedroom at the focal plane. You feed that messy, leaked light into the wide end of the photonic lantern,
which acts as an optical funnel, untangling the overlapping waves into pristine, single-mode fibers while preserving the phase.
And finally, you take that phase data, feed it into a computer, and run quantum-inspired algorithms to digitally cancel out the last remaining bits of starlight via destructive interference.
That's the entire process from start to finish. And if the system works as engineered, what you are left with is a clean, definitive stream of photons belonging entirely to a potentially habitable world.
You have successfully conquered the 10 billion to 1 problem.
You've beaten the floodlights.
This all sounds incredibly futuristic. I mean, we're talking about manipulating the phase of light in microscopic glass funnels to digitally cancel out the glare of a star trillions of miles away.
It sounds like sci-fi.
But what grounds this entire conversation is the timeline. This isn't science fiction slated for the year 2300, is it?
Not at all.
We are talking about prototypes being built and tested right now, today.
That is what makes this research so urgent. The PEEPSS project is not just theoretical math on a chalkboard in a university basement somewhere. No, they are currently in the middle of a focused, heavily funded 3-year effort. If you walk into the CREL laboratories at UCF right now, you will see graduate students actively fabricating these photonic lantern systems.
Actually building them.
Yes, they're placing them on optical benches, running lasers through them, inducing artificial aberrations, and proving that the phase recovery and destructive interference work in the real world.
And it is moving beyond the sterile environment of a laboratory cleanroom, too.
Oh, absolutely.
They were actually putting this hardware on real telescopes, dealing with real starlight.
Yes, versions of this technology have already transitioned out of the lab. Through collaborations with groups like the Air Force Research Laboratory and various international partners, they've deployed early prototypes on actual mountaintop telescopes in Hawaii.
So they're battle testing it.
They are battle testing the glass against the real atmosphere, real thermal fluctuations, and real stellar photons. They are proving that the dirty bedroom problem can be solved in the field.
But a mountaintop in Hawaii is just a proving ground. The ultimate goal, the true finish line for all of this astrophotonic development is getting this technology integrated into something much, much bigger.
The Holy Grail.
We are looking toward the next great leap in space-based astronomy.
We are. Everything we've discussed today, the coronagraphs, the lanterns, the quantum imaging, is laying the critical groundwork for NASA's proposed flagship mission.
The Habitable Worlds Observatory, HWO.
The Habitable Worlds Observatory. They didn't mince words with that acronym. It tells you exactly what its priority is.
Right. It's a mission with a singular historic focus. The HWO is currently in the rigorous planning and development stages.
Yes, it is.
And it's being designed specifically with the goal of not just finding Earth-like planets beyond our solar system, but crucially analyzing the atmospheres of those planets for the chemical signatures of life.
Biosignatures.
Biosignatures, right.
Yeah.
They want to look at the light from the planet and see if there is oxygen, methane, or water vapor in the air.
Exactly. They are looking for gases that are wildly out of equilibrium. The kind of atmospheric chemistry that can only be sustained if a biological process like photosynthesis or microbial respiration is actively pumping those gases into the air.
Because otherwise those gases would just break down, right?
Right. They react and disappear if something isn't replenishing them. But to get a clean enough reading of that atmospheric spectrum, the HWO is going to need the absolute best optical technology humanity can muster.
It cannot afford to have a blind spot in the non-common path.
It cannot afford the dirty bedroom. And it certainly cannot afford to be blinded by that 1 in a million stellar leak.
Which is exactly why the work being done at UCF and Sydney and Santa Cruz is so vital right now.
It's the linchpin.
If these researchers can prove that photonic lanterns and the PEEPSS architecture can reliably solve the extreme contrast problem, this astrophotonic technology could become the central beating heart of the Habitable Worlds Observatory.
It could be the literal lens through which humanity finally sees another Earth.
It is a testament to human ingenuity. I mean, we are looking at a problem that seems mathematically and physically insurmountable, a 10 billion to 1 floodlight blinding our view of a tiny firefly, and we are quite literally engineering our way through the noise.
The stakes of this endeavor simply cannot be overstated.
Let's focus on those stakes as we wrap this up.
Yeah.
Because Stephen Eikenberry made a comment that frames the weight of this research perfectly.
Oh, I know the quote you're talking about.
It's so good. He pointed out that just identifying habitable worlds around other stars, just proving that there are rocky planets out there with the right temperature and conditions where Earth-like life could potentially survive.
Just that alone is a paradigm shift.
Right. That rewrites the textbooks on planetary science.
But he takes it a step further, and this is where the gravity of the mission really hits you.
Go ahead, lay it out.
He said that if this technology works, and the Habitable Worlds Observatory uses these photonic lanterns to detect actual, verifiable evidence of life, if we find a strong, undeniable biosignature in that atmospheric data, then we are talking about one of the greatest, most consequential scientific discoveries in the history of our species.
It is a staggering thought. And it brings us all the way back to the backyard looking up at the sky.
Yeah.
Eikenberry summed up the reality of this exact moment in time with a quote that I haven't been able to stop thinking about. He said, "We are one mission away."
One mission.
Just one mission away from ending millennia of philosophical speculation. We'll look up and know.
We'll look up and know. I mean, for the researchers in the clean rooms right now, meticulously stretching microscopic glass fibers over open flames, that is the reality that drives them.
It's not just a job.
No, they aren't just building a sensor for a telescope. They are building a bridge across the existential unknown. They are building the machine that answers the oldest question we have.
Which leaves you with a massive thought to mull over as you step outside tonight and look up at those stars.
Yeah.
We've spent this entire time talking about the physics, the diffraction, the optical leaks, the photonic funnels, the quantum algorithms.
The nitty-gritty engineering.
But let's assume the engineers win. Let's assume NASA's Habitable Worlds Observatory launches with this technology on board.
Okay.
It deploys 1 million miles from Earth. It points its perfectly polished mirror at a distant star. The physical mask blocks the glare. The photonic lantern untangles the microscopic leaks. The algorithm mathematically erases the noise, and the data beams back to Earth.
And it's positive.
And it's positive.
Yeah.
The methane and oxygen are there. We succeed. What does humanity do on the very first day that we wake up, look at that night sky, and know for an absolute, undeniable fact that something is looking back?
That changes everything.
What happens to our philosophy, our society, our place in the universe the day after we are officially no longer alone?